Hey, Dr. Scott Stevens here to talk to you about linear regression. What's really going on? The mechanics of linear regression are fairly straightforward, but exactly what the answer means and the work that we do with it can be a little more subtle than that. So that's basically what this slide shows about. It'll probably have two parts. The first one giving you a setup of what's going on, the idea, and then showing how we do it in Excel and how we get the information that we need to draw good conclusions about the results of a linear regression. So let's go ahead and get started. You remember how linear regression works. We start out with two variables that are probably related to one another. We graph one of them on the x-axis and one of them on the y-axis, and we look at the scatter plot to see if it looks like there's a relationship. In particular, with linear regression, we're looking for a linear relationship, a straight line relationship. The points in this graph here certainly don't all lie perfectly on a straight line, but we can kind of get a rough idea of where the best line should be. It's about like this, and it has an equation. Its equation is in fact this. The numbers in yellow give you the slope of the line and its y-intercept. So every time we go over 1, we're going up about 0.01 in this graph, and where it crosses the y-axis, right here, is about negative 125.9. That's great, but there's more to it than that. Let's take a closer look. And to do so, we really have to go to 191. The idea of estimation. Remember how this worked. What you have is a sample, and you're trying to draw conclusions about something in the population. For example, you might know the population mean. You might want to know the population mean, but you don't have the entire population. All that you have is a small subset of it, a sample. So what you'd like to know is what's the population mean, and you're going to approximate it by finding the sample's mean, x bar, and use that as an estimation of the population mean, with the idea that the estimate, x bar, will probably be close to the population parameter that you want to know, mu. But that sentence includes two weasel words, probably and close. What does it mean to say that it'll probably be close to the population parameter? For example, I could say the population mean is probably between 12.3 and 14.5. That range specifies what we mean by close, and the range is called a confidence interval. As far as probably, well, when we specify a confidence level, we are going to say essentially how reliable is the procedure that we use to find that estimate. If we follow our confidence interval building procedure with a random sample, the confidence level is what fraction of the time that resulting interval will actually contain the value that we're looking for. Look at this a bit more carefully. What does 95% confidence in the interval really mean? Well, it's kind of like catching butterflies with a butterfly net. Even though you're using the same technique and the same net each time, sometimes you capture the butterfly, sometimes you don't. In the same way, when you build a confidence interval, sometimes that interval captures, that is, it contains the population parameter that you want, but sometimes it doesn't. The fraction of the time that it works, the fraction of the time that your interval captures the population parameter, is the confidence level. Well, how big is the confidence interval? That's the size of the net that you're using, if you like, in your butterfly example. A big wide net has the advantage of having a good chance of capturing the butterfly. A big wide interval has a good chance of capturing the population parameter that you want. But the downside is, it's a wide interval, and so it gives you a less precise estimate of the quantity you're interested in. Imagine it this way. You're going to go downtown and get some food with a friend of yours, but they're currently finishing up their homework, and you want to know how long is it going to take them to get done. They could give you three answers. Here's one. I'm 99% sure that it'll be done before 8 a.m. tomorrow morning. Very precise, 99.9% sure, but a very wide interval. Or there's this. I'm 90% sure that I'll be done in somewhere between 10 and 15 minutes. They're pretty reliable, pretty sure, 90% likely, and the interval's fairly narrow. Here's the third one. I'm 10% sure that I'll be done somewhere between 12.3 and 12.4 minutes from now. Well, here the interval's extremely narrow, so the answer is extremely precise, but it's hardly ever right. The procedure that was used to generate this interval will only give you a correct range 10% of the time. So I think most of us would agree that the middle one is a trade-off between reliability in terms of confidence level and usefulness in terms of the narrowness of the confidence interval. All right, but what does all of this have to do with linear regression? Well, basically, it's just like 191, and we need to worry about confidence intervals. We're going to use our sample to find the best straight line through our set of data points, but we're actually looking for the best straight line through all of the data for the entire population. So the m and b that we find are only going to be approximations of the actual values of m and b for all the data. And that's the job we have to do. It goes something like this. Linear regression assumes that we begin with a perfect straight line relationship between the values of x and the average values of y. They fit on a straight line, so if you know x, you know what y is. But then we're going to take each of these bumps, these dots, and bump them either upward or downward. The amount of the bump is going to be normally distributed with a fixed standard deviation and with a mean of 0. So a dot is likely to be above the line as below. Every dot has its own independent bump, either up or down. They're all independent, and they all come from the same normal distribution. Here's the point. Given the dots, there's the red line and the dots that came from it, but we don't know the red line. It's what we're looking for. All we actually have are the dots. So we'll proceed by finding the best straight line through the dots, like this, and know that that line is probably pretty close to the best straight line that we're actually looking for. Again, the one here in red. The blue line that we see there is actually the best guess for the red line. It is the line in the linear regression line is the one that gives you the minimum MSE, mean squared error, for all possible straight line forecasts. There's no straight line that matches the blue dots better than the one that we're going to find. And we can show that if you use that line, given the assumptions of the model, it also makes this line a maximum likelihood estimator, which means this. If those blue dots came from some straight line, what's the best guess as to the straight line that they would be derived from? Well, that's the same line that you find. Statisticians like maximum likelihood estimators a lot. So, how much can we trust the line? Well, we're going to have a confidence interval for our slope. We're going to have our confidence interval for our intercept, b. The calculations themselves are kind of complicated, but Excel's happy to do them for you. All your job is to interpret them. And we have to get Excel started by telling it where the data is and what the confidence level is that we want. That's going to be some Excel work, so I'll put that in a separate presentation. Go ahead, please, and watch linear regression in Excel. Thanks a lot.